everybody. So I'm making this video on this problem on one of your homework sets. So it says you rub two 4-milligram balloons with a wool sweater. The balloons hang from a 0.5 meter long very light strings. So the strings are massless. We don't have to worry about them. When you attach the strings together at the top, the balloons hang away from each other, each string making the angle of 37 degrees with the vertical. So it says, represent the situation with the force diagram for each balloon and determine the magnitudes of the forces on the diagram. Okay, so let's see. Well, I drew this right here. So I just drew kind of an idea of what is going on here. I'm going to draw a force diagram for just one of these. And let's see, I'll draw it off over here. So I'm going to say, I'm just going to do one of these right here, this one. And so that's going to be drawn over here. So this is this balloon is the, or I guess I should say the balloon is the dot. So the balloon right there. And so the forces here, well, there's going to be a tension force due to the string. So there's a tension force due to the string, and it points like that. So that's a tension force. There's weight pulling this thing down. That's going to be mg, the mass times g, not to be confused with this mg, which is milligrams. So this is the mass in milligrams. And that converts to 4 times 10 to the negative 6 kilograms. So, okay. And then also the other force then is going to be the whole reason that these two things are repelled is there's an electric force, or there's a force from the other balloon that's pulling it this way. So there's this electric force like that. And so I'm trying to calculate the magnitude of determine the magnitude of the forces in the diagram. Okay. Let's see. So I have one of my vectors is kind of pointing at an angle here, so I'm going to need to break it into its components. So to break the tension force into its component vectors is going to be this one. This is going to be the tension force in the x direction. And then I got this one here. This is going to be the tension force in the y direction. And then the angle, so if you can see, I got my tension force goes along the rope here, and then tension force in the y direction goes like this. So I can use a little bit of geometry. This angle here, which is the 37 degrees that they told me about, 37 degrees with the vertical. So here's the vertical here. So you can use a little bit of geometry, right? If you got two parallel lines and then there's a segment in between there, I can say that this is the same angle right there, which is this angle right here. So this is theta right here. So with that, I can then use Newton's second law. So let's write out FTY. So FTY, using a little bit of trigonometry, this is going to be the magnitude of the tension force times, what would that be, cosine, right? Yeah, cosine of theta, and then FTX is going to be the tension force sine of theta. So if you're bothered by that at all, so remember, right, that I can make a triangle like that, and then you can use a little bit of trigonometry to get that. But now I'm going to then use Newton's second law to keep moving here. So I got F net equals ma. This balloon is at rest, so the acceleration is going to be 0. Well, it's not just at rest, it's not accelerating either, it's just, well, it is at rest as well. So the acceleration is going to be 0, so on the right side of the equation is going to be 0. And then F net in the, let's start with the vertical direction, is going to be FTY minus mg, because mg is pointing down. And then FTY, I said, was FT cosine theta minus mg equals 0. Sorry, that should be equals 0 over here on this side too. Let's see. So I know the mass, I know g, I know the angle, so I can find the tension force. So I'm just going to isolate the tension force now. That's going to be mg over cosine of theta. My mass, I converted it over here. It's 4 times 10 to the negative 6. So that's milligrams in converted to kilograms. G is 10 newtons per kilogram. I'm going to forego units for simplicity's sake. And this is cosine of 37. So that means then that the tension force is going to be 4 times 10 to the negative 6. So that's times 10. Oh, sorry, I'm using, instead of 9.8, I tend to use, I round to 10. That's just something I do. Hope you're okay with that. Divided by cosine of 37. So that's going to be, I'm getting about 5 times 10 to the 1, 2, 3, 4, 5. I think negative 5 newtons. So that's what I'm getting for my tension force. And then the weight. Well, the weight is, so I got my tension force. I just need now to get this electric force. But the weight, yeah, the weight is just going to be mg. So the weight, which is the gravitational force, that's just going to be mg. So the gravitational force is going to be 4 times 10 to the negative 6 times 10 newtons per kilogram. So that means Fg is going to be 4 times 10 to the negative 5 newtons. So that's my gravitational force. So I got the tension force, 5 times 10 to the negative 5. I got my gravitational force, 4 times 10 to the negative 5. Now just to find out what the electric force is. So for here I can use that the electric force is going against the x component of the tension force here. So I'm going to keep going with my Newton's second law, but just do it now in the horizontal direction. So I got the tension force in the x direction pointing to the right, minus the electric force pointing to the left. And then again, my acceleration is going to be 0. This is at rest. There's no acceleration. So that's what that's going to be. This is going to be 0. So the tension force in the x direction, according to what I have here, is going to be Ft sine of theta. So this is going to be Ft sine theta minus my electric force is equal to 0. Isolating for the electric force then is going to be Ft sine theta. I know my tension force already is 5 times 10 to the negative 5. Is that what I had? Yeah. And then times sine of theta, so it's sine of 37. So this is going to be three times 10 to the negative 1, 2, 3, 4, 5. Yeah, 3 times 10 to the negative 5. I suppose I could have used this like it looks like a 3, 5, 3, 4, 5 triangle, but nah. It's more mindless for me to do it this way. So here we go. There's the electric force then. So I got the electric force, the tension force, and the gravitational force. Hey, 3, 4, 5, right? Cool. Awesome. So we got that. So that was the free body diagram of this one. This one over here, the free body diagram would look exactly the same, except, so if I wanted to draw it, let's see, I can draw this one to the left side. I'll just draw it really small over here, just so we get the idea. Free body diagram here, you would have, again, mg, because the masses are the same. Tension force would be the same, Ft, but it's pointing now in this direction, it points along that direction. And then the electric force would be pointing like this, because this is the two balloons the two charged balloons interacting with each other. So that's that particular free body diagram right there. So wow, oh, that was part A. I hope part B isn't as long. What can you say about the magnitudes of the forces that the balloons exert on each other? Well, the magnitude, so I have one object here, and they're both exerting a force Fe on each other. If I called this object 1, let's see, if I called this object 1 and this one object 2, right? This Fe would be the force that object 1 exerts on object 2. This would be, so 1 on 2. And this Fe would be the force of 2 on 1, right? Oh, 1 on 2 and 2 on 1. All that sounds really familiar. So we got two objects interacting with each other, and there's one of those laws, I think it's Newton's third law, right? So, and it says that, you know, basically the force that object 1 exerts on object 2, right? Forces come in pairs. So the force that object 1 exerts on object 2 is equal to the same magnitude but opposite in direction force that object 2 exerts on object 1. So in other words, the magnitude then of these forces should be equal. Because this is an example of Newton's third law. Awesome. And then it says, will the relative magnitudes change? So I think they mean of the forces, the relative magnitude of the forces change if the charge on the balloon is 2 times larger than the other. How do you know? And my answer to that is no, they're not going to change because Newton's first law is still going to hold. If this is still, so it doesn't matter if I jam a bunch of charge onto this object, the force that object 1, and we're talking about the forces that these 2 balloons are exerted on each other, that's this electric force. It doesn't matter how much charge I put on one or the other, the forces will always be equal. The force that one object exerts on the other is equal to the same magnitude that that those forces exert, just opposite in direction. So yeah, and we're going to see another kind of, so that's one justification of it. You're going to see another justification of this though once you guys do Coulomb's law, and you'll see another reason for why those forces will end up being equal despite which object has the greater charge. All right, so I hope that helped. All right, bye.